All right. We are looking at photoelectron spectroscopy here. This is another of those analytical devices based upon how he determined how many electrons there were in each of these. So a little sample is exposed to some electromagnetic radiation. Electrons jump out in the sample. They go around, get collected by this electron multiplier, and gets recorded. So this device helps us understand how things are going to be used in electrons. So this is another example of reading some graphs and understanding and being able to read and determine what they look like. So you have a graph. So if you have your nucleus down at the center, there it takes energy to remove an electron. It's called the binding energy. And so the closer an electron is, the higher the energy is. Now here's the difference to what you're not used to. We're used to seeing as you go to the right, things get bigger. It almost always increases to the left. So as you are closer, these electrons, which are going to show up as little peaks, are going to be higher energy needed to remove than things further away from the nucleus. This y-axis is the number of electrons. So you can see the taller the peak, the more electrons. And they are very representative. It looks like about twice the amount. It'll be generally 2 electrons, as you'll see that. So when we look at example of hydrogen, it's going to have so much energy, and it's going to be 1 electron in the 1s, because again, they're going to fill up with highest energy as your 1s, then your 2s, your 2p6. We talked about energy and how they fill up. Again, helium with its 2 electrons is going to be twice the peak, because there's twice as many electrons. So again, we're just trying to get an idea on how to read these examples. So they each have, this one has 1 proton, so you can see its energy is, midway. This has 2 protons, and because there's 2 protons, that means there's a higher overall charge. So therefore, it's going to be more energy needed to remove the 1s electron in helium, more tightly held because there's a higher effective nuclear charge. So remember, highest energy would be like at the origin. But remember, it's not the origin because that's not 0. Energy is going to be increasing across. It doesn't always show you the numbers, but we will see some examples where they will have that. So if we think of oxygen, this radial example is to help you see kind of the different electrons. Your 1s2, they are the closest. They're going to need the highest energy to remove it. 2s, they're further away. You can see there's 2 electrons in comparison, because these are kind of comparative peaks to each other. So these should be equal, but because it's further away, it's going to require less electrons. In the 2p, they're even further away than either s electrons, and there's 4 of them, so twice the amount of electrons than you would find in either s. So all of this hopefully is making sense as you have there. Please, of course, ask questions as you have them. I'm here to help. But of course, we think of as you get further from the nucleus, you're going to have the different peaks for the different sublevels. So we look at scandium with its number of electrons. All right, we've got that 1s2, 2s2, this is making sense, 2p6, further energy, 3 times the height, 3s2, yup, 2p6, or I should say, I think that's supposed to be 3p6, 3p6. Then we have the D. We see the D is ahead of the S. You think, why are these out of order? Well, 3D is lower energy than 4S. So even though D fills up after S, energetically wise, once there's an electron there, it is closer to the nucleus. Therefore, it has higher energy needed to be removed. Okay, so keep that in mind. Keep that in mind. Again, this is not how they fill in normally. Now, again, early on, yep, that's the way it's going to be. But this is talking about removing electrons. So there's higher energy because it's in a lower energy level. Plus, the 3D shield the 4s, so it's easier. It takes less energy to remove the 4s electrons compared to the 3D. Okay, so this electron shields this over here because it's on the inner side. So example, why is one peak much larger than the other? So why is this one larger? What element is this? These are questions that all come up on your AP exam. You know, sodium. Okay, it's sodium. How do we know that? Well, I see 4 peaks. That's your 1s2, 2s2, 2p6, 3s, not quite 2, but a 3s1. So I'd see that that would have 11 electrons. And therefore, again, your first peak is to help compare the other peaks. The peak represents 6 electrons. The other peaks only represent 1 or 2 electrons. Which sublevel are the electrons peak A in? If this is peak A, that shouldn't be 3s. That should be 1s. 1s. I think my things got moved over when I translated it. So the sublevel the electrons are peak A in, that'd be the 1s, because that's closest to, that's the highest amount of energy needed because energy is increasing this way. Okay, so always make sure you read your axes to see which way it's going to be directed. Now, example 2, you got a PES data shows only the peak for the 1s electrons. Why is the peak for nitrogen further to the right? So nitrogen, oxygen, right? Nitrogen has 7 protons, oxygen has 8. So this is just looking at the 1s electrons, the ones closest to the nucleus. Well, oxygen has higher number of protons, therefore higher effective charge. Or you could say oxygen has a lower effective charge. So we see that nitrogen, this talks a little bit more in depth or attributes a atomic radius, but it has a lower effective charge because it has less protons than oxygen does. So it has less of attraction between the nucleus. And you could also think about how it's actually further away, because nitrogen would be further away, its outer electrons would be further away, therefore its inner electrons would also be a little further away as well. But I would stick with the idea of the effective nuclear charge and the number of protons, because that is what's attributed to before we talk about periodic trends, which is the next unit. I believe last example, yeah. Draw the expected PES spectrum. Doesn't need to be great. So boron, you got your electron configuration. Good. Figure out how many peaks. Well, there's 3 sublevels, so there's got to be 3 peaks. Sketch the first one. Remember that is going to be your reference point as 2 electrons, so they should be the same, and 1 electron. Now, as far as this gapping, it doesn't need to be great. It doesn't need to be, like super exact. However, your 1s is going to be highest energy, then further out, then further out. That's what they're going to be really examining. So make sure that you come in with any kind of questions, get some practice, and let me know what questions you have. Take care.